So 1.3 is all about measuring and classifying angles. So again, it's a lot like 1.2 with where we did segments, but we're going to do similar things with angles today. So for today, we have kind of 3 objectives: name and classify angles. So naming angles is going to be a little tricky. When we say name, we mean using geometry notation to write them out. We're going to talk about measuring angles and angle bisectors. We're also going to throw in some algebra in there. I don't know how far we'll get. And third thing is, let's try not to set your computer on fire in frustration at the monotony of Zoom. So this can be pretty difficult to go through on Zoom, and try not to get too frustrated. All right, defining an angle. A little brainstorming here. Thank you, Jalissa. Make sure to type your first name and last name in the attendance if you haven't done so. Defining an angle. So I just want you to think about this for a second. How would you describe an angle? So if someone asked you, what's an angle? What would you say? Second question, how is an angle made? What is an angle made of? What are the parts? So think about these things. If you want to sketch out a picture or something, that's fine too. Just take a minute and think about it. Try to activate some prior knowledge about angles. Okay, I know I didn't give a lot of time there, but just in the interest of getting through things. So an angle is formed by 2 rays. We call those rays the sides, with a common endpoint. There's a little bit of vocabulary here that isn't on this slide. So these rays, again, angles aren't always going to be drawn with rays. Sometimes they're just going to be segments, or maybe they'll even be full lines. But technically an angle kind of extends forever, even if it has endpoints with that. We call these the sides. So both of those are the sides of the angle. And this common endpoint, usually we use the word vertex. Or if there's multiple vertexes in a picture, there's another word, vertices. But vertex is our common endpoint, sides, and the angle is kind of the space in between them and the sides. It's kind of this whole thing. When we're measuring an angle, we're talking about sort of is the space in between, how many degrees make up that space. All right, let's clear that and move forward. Okay, so there's a few different ways that we can name an angle. And when I say name, I'm talking about, oh, jumped ahead of myself. Interior of an angle, the interior is between the 2 sides, exterior is outside. In general, all the angles we're going to be working with fall between 0 and 180 degrees. So the interior will always be in here, less than 180 degrees, and the exterior will always be out here, bigger than 180. Not that important. We'll get into measurements here later. A little bit harder is naming. So there's really 3 ways that we name an angle. It really sort of depends on what labeling exists on the picture. So in this, we have some points labeled. We have this little number 1. For this one, if there's a number in the angle, the easiest way and the most clear way to talk about an angle is just to use that little 1 or any number that might be there and just call it angle 1 or angle whatever number happens to be there. So that's kind of the easiest way. That little symbol that looks like a small acute angle right down here is our angle symbol. And so that refers to this angle right here. That's kind of the easy way. And it's one that I'll recommend using quite a lot. I may even just add numbers into my picture in the angles just to make it easy to talk about, because the other ways are a little bit harder or a little more confusing, or even if they're not hard or confusing, they just take a little longer to figure out what angle we may be talking about. So that's the first method, and highly recommend that one. The second one, which is also easy but can be confusing, if there's only a single letter with the same vertex, so in this case there's only one angle here with R as the vertex, then we can just use that letter. We can call it angle R. Again, also very easy, but this one you'll see doesn't work very well in some situations. So angle R, again, also very easy, just as easy as calling it angle 1. But we'll see this one is a little less good, and this one I won't use very much. Because if we have a picture like this and we say angle R, well, there's a lot of angles here. Which one are we talking about? If we say it's angle R, do we mean that it's this angle up here? Is this angle R? Do we mean this angle down here? Is that angle R? Do we mean this one over here? You kind of see the point, right? If there are multiple angles that have the same point, it's confusing to call them all R, because which one are we actually talking about? So in a case like this, one thing we could do, and what I'll do on pictures a lot of times, is I'll just put numbers here. I'll call this 1, 2, 3, and 4, something like that. That way it's easy, and I don't have to call them all R. I can say this is angle 1, this is angle 2, this is angle 3, this is angle 4. It's a little bit easier. But sometimes that doesn't even work. There are some situations where that's not great either. If you want to talk about two different angles that maybe overlap each other a little bit, then you can't label them with numbers very well. So that's where we're going to have to get into this third method. And the third method is to use some points. Who knows? Yes. We don't know which one is R. The third method is if there are 3 points here, and most of the time there will be, most of the time we'll have points labeled, we can use these 3 points to talk about our angle. So if we kind of trace the shape of the angle, we'll follow along 3 points. We have S, and we have R, and we have T. So we can call this angle SRT. It's really important that they're in this order or another similar one, because if you follow those letters, you follow those points, you kind of trace out the angle, right? If I follow them, I go SRT. It makes the angle when I trace those points. The middle letter has to be the vertex. So when you're looking at one of these namings with 3 letters, which letter is in the middle tells you which letter is the vertex, which point is the vertex of the angle. R, that one's the vertex. Alternatively, we don't have to do SRT. We could go the other direction on this. We could do TRS, right? Follow the angle this way, TRS, and we could call it angle TRS. Either one of those is totally fine. And sometimes using these 3-letter namings is really the only way to do it. I'll kind of show a little picture here of why we might do that. And it has to do with overlapping. So if you have some angles, like, so here's a line, and you have you want to talk about some parts of these angles that overlap, or well, actually, let me draw another line in there. This will make more sense with another line even. Okay. There's a lot of angles here. So if I wanted to talk about angles like this angle here, and then another one, which would be something like this angle right here, you can see how they kind of overlap in the middle. And there's not a way that I can draw a number in there to write an angle number. I couldn't draw, I mean, I could, but it would be unclear where that number kind of goes. So in this case where they overlap, I'm gonna have to use this three-letter naming. So hopefully I have some points out here and I can use those to kind of label it. So this pink angle, I could name it like CAE. But there's not really a good way for me to write a number to mark CAE. Or the other one, the green one, I could do like BAD, for instance. When they're overlapping like this, we kind of have to use that 3-letter naming. which is unfortunate because it can be a little confusing to read and it takes a second to figure out which angle you're trying to talk about. But it works all the time, so it is something we will use. All right, so that's kind of the naming. I know that's just presenting it to you. It'll take a bit to get that down because it is a common thing. Now, to reiterate that whole order thing, you want to make sure this angle here that we have drawn that we've been talking about, we could not call it STR. Those are all points that are part of the angle, but if you follow those letters, if you go S, then T, then R, that's not the same angle as what's pictured there, right? So the letters have to follow the shape of the angle. And so if I follow these letters, it obviously doesn't make the same angle, so it's not properly named. So make sure we don't do that. All right, so now that we can name them, the other thing we want to be able to do with angles is measure them. So we are going to measure angles in degrees. So one way that a degree is defined is 1/360th of a circle. Funny thing, you know, right? The reason we use 360 for a circle, it seems like an odd number. Not that it is odd, but a number. Why would we choose that? Is because 360 is sort of roughly the number of days in a year. And the reason they don't choose 365 is because 365 is not quite as nice and even of a number, even though that's technically the number of days in a year. And some ancient mathematics, they actually use 365 degrees because that matched the number of degrees and number of days in a year. So kind of has a correlation to an actual real thing. We choose that number for a reason. A circle is 360, and you probably know that. So we had a ruler postulate last time, which basically said that we could measure segments. We're allowed to give measurements and coordinates to segments. Today we have something called the protractor postulate. Again, it's a postulate. We kind of accept it to be true. It sounds really dense. I'm going to read it, but I'm going to interpret it for you here in a second. Given AB, a line AB, and a point O on AB. Let me just go ahead and sketch that out. So we have a line AB and a point on this line called O. So we'll call it there. All rays can be drawn from O, can be put in a one-to-one correspondence with a real number. So it's saying we can draw a bunch of rays from this here. And all of these rays create different angle measurements. And those angle measurements are going to be numbers between 0 and 180, which represent the half of the circle that gets created here. So all of this together, we go from 0 degrees all the way over to 180 degrees. So all of these rays represent different angles from 0 to 180. It's essentially telling us that angles exist, we can measure them in degrees, and they go from 0 to 180. So all of these angles would represent different degree measurements. And technically there's kind of an infinite number of rays that we can draw here, so we can have any angle we wanted that's in between 0 and 180. It's a really dense thing, but that's all we really need to understand, is that we're going to measure angles from 0 to 180, and we're allowed to do it by this postulate. Okay. So if you didn't know what a protractor was, this is a protractor. A protractor is used to measure angles. So up here we have a few angles drawn on this protractor. The protractor has a scale. On the outside, it goes from 0 to 180 along this way, from left to right. And on the inside, it goes from 0 to 180 from right to left. It's just so you can kind of measure from either side and still get an angle measurement. So when we're finding a measure of an angle, the measurement of an angle, in symbols, we write it out like this. We have this little M here. That stands for the measurement of angle COA. And when we talk about that, we generally want to know how many degrees it is. So let's use this protractor up here to find a few of these angles. So I'm going to kind of go through them. So the first one, we're looking for the measurement of angle BOD. So I can follow it with the letters and I can see what that is. So BOD, that's this one right here. I want to know what this measurement is in between it. So I can kind of measure the number of degrees that are marked out here on my protractor. And this one's nice and easy, and this is the way we would want to line up a protractor if we were actually using it. We'd want to line up one of the sides of the angle along 0. This is 0 down here. And then we can count up to figure out where the other side of our angle is. So the other side of our angle is marked at 65 degrees. Yep. So we would say this is a 65-degree angle and be done with it. And then we can kind of look at one of the other ones. So the next one, we have angle COA, right? So COA. So that's that angle right there. I kind of follow it. Yep, and I'm already seeing the answer in the chat, 45 for sure, right? Now this one, I'm going to be using the inner scale, just because that's the one that has 0 on it right here. So 0 all the way up to 45. So those ones are pretty easy to measure because my scale was lined up nicely. The last one is only slightly trickier just because of the positioning of everything. Since I'm doing angle DOC, let's DOC, that's this one right in here. So I want to figure out how many degrees are in here. Yeah, Jalissa, you're saying 70. So yeah, I think that is the answer. We kind of just have to count along there. So if I count it, it looks like these are all counting by 5s. I could do that. I could say it's 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 55, 60, 65, 70. Yeah, so 70 degrees in there. Generally, when you're using a protractor to measure an angle, you want to go ahead and make sure it's lined up on 0. But you can use the units along here to figure that out. And one thing to really know and understand here is whenever we have a full half circle, a full arc here, in total it represents 180. So once we knew these two angles on the side, we could use those to figure out this one without actually counting it. Yeah, exactly. I could add the ones that I know and take that away from 180. Yeah. So that's another way that we could for sure do that without actually just counting the units on there. Totally up to you in terms of what you would want to do. Personally, I would just line if I had a protractor and I was measuring this, I would just line it up correctly and use it that way. But it doesn't really matter. All right, moving forward, we have these types of angles. So I'm assuming you already have some familiarity with this. We have the acute angles. Acute angles measure greater than 0 degrees and less than 90. So they're going to be in between there, 0 to 90, right? They're kind of small, narrow angles. Then we have the right angle. We use right angles all the time, especially when we build stuff, right? Our rooms usually have right angles, and the floors and the walls are hopefully close to a right angle. They're also really useful geometrically because we're gonna be wanting to have right angles to use things like trigonometry and such later on in the year. Then we have obtuse angles. Those are bigger than 90 degrees, wider than 90 degrees, but less than 180. And then finally, you have the straight angle. Straight angle is basically a straight line, and a straight angle measures 180 degrees. Really, we're going to want to always notice when we have a straight line. That's going to be really useful because then we know that we have 180 degrees here. And that can kind of help us do some problem solving. So we'll always want to notice whenever we have a straight angle because it will help us figure certain problems out. Next here, we want to talk about congruent angles. So two angles can be congruent. Remember, congruent means same shape and same size. So two angles are congruent if they have the same degree measurement. So if we have angle ABC is congruent, that's what that symbol means right there, to angle DEF, what that means is that the measurements of those angles are equal. So if one of them is 50 degrees, the other one has to be 50 degrees. We don't care if they're exactly the same size, and what I mean by that is maybe one of them is done with some lines, and it's a very large looking angle, and this is like 50 degrees, and another one is done with just some small segments or something. As long as the measurement is the same, we don't care. We can still say that they're congruent because they're both angles and they have the same measurement. So they fulfill all of the properties of two things being congruent. Okay. Also works the other way. If we know that two angles have the same measurement, then that means they're congruent. The way that we mark congruent angles on a picture is we use these little arc marks. So if we want to show that these two angles were congruent on our picture, we would make arcs in there. Now, if we had another set, just like with segments, where we would do 2 tick marks, for angles, we use 2 arc marks. So if there's another set of congruent angles, we'd use double arcs. Or if there's a third set, we'd use triple marks. And it could get out of hand, but generally we don't need more than that. All right. And then finally, we have what's called the angle addition postulate. We're going to use this a lot. We're going to use this to set up algebraic equations involving segments. But for right now, we'll focus on what it is and just some simple numbers. So if S is in the interior of angle PQR, so we have a point S inside of this angle, then the measure of, keep doing that, the measure of PQS plus SQR, that's funny. They're color-coded, but they're color-coded wrong. PQS is actually the red one, even though it says it's blue there. And SQR, right? Those two angles have to add together to equal the whole angle. Essentially what we're saying is, I'll use this in some simpler letters. Instead of using all of these PQRS, let's go ahead and just throw some numbers in there just to make it a little easier to talk about them. So if we call this angle 1 and angle 2, what we're saying is angle 1 plus angle 2 has to equal the whole thing. It's that easy. That's what the angle addition postulate says. That's just like, remember the segment addition postulate, when you had a segment that was cut into pieces, we said this part plus this part has to equal the whole thing. So it's the same idea as the segment addition postulate, but we're talking about angles. This is Mr. Bechtel's touch. You can laugh at it if you'd like. All right, this is pretty dry. Let's actually just look at an example. Let's see what it looks like right here. So we have the measurement of angle XWZ. So XWZ, that's the whole thing. Sometimes when you have a picture like this, if you want to talk about the whole thing, what I do is I label it at the vertex. So I label it as 121. That tells me that I'm talking about the whole angle, because it can be difficult to mark that and to show that. So I just label at the vertex what the whole angle would be. Again, it's not that clean, but it just kind of helps me figure it out. And the measure of XWY, so that's this angle right here, XWY. That one is 59 degrees. Well, and then we want to find this other one. We want to figure out what this angle measurement is over here. we could give it a variable if we want, or we could just kind of think about it. Well, the angle addition postulate says that these two angles have to add to be equal to the whole. So if I called this, let's give it a variable. Let's call it, I don't know, A for an angle. I could set up an equation for myself using the angle addition postulate. I could also do something much easier than this, but that would only work if I have numbers. So I'm just going to set up my equation. So 59 degrees plus A is going to equal 121. Very simple equation. I just subtract 59 from both sides to figure out what my angle needs to be. 62 degrees. So this angle right here is 62 degrees. Again, I could have just jumped straight to subtracting them. If I know the whole thing is 121, part of it is 59, I just subtract those and that'll tell me what's left over. But in the future, we're going to look at problems where these are not just numbers, they might be algebraic expressions. And so if they're algebraic expressions, we'll want to make sure to set up an equation in those cases. So, but either way, in this case, the answer is 62 degrees. I'm going to do one more slide. We have 4 minutes remaining. All right, last thing is the angle bisector. So hopefully yesterday, or not yesterday, but our previous lesson, we remember what the word bisect means. Bisect means to cut into 2 equal parts. So for a segment, a bisector, an example of a bisector was like the midpoint. The midpoint divided the segment into 2 equal parts. For an angle, what we're going to have is some line or ray or part of a line that cuts our angle exactly in half. And those will be called angle bisectors. So you can see in this picture, we have our angle LJM. And this ray right here is cutting it exactly in half. So that means if it's exactly in half, that means that these 2 pieces would be equal measurements. And just like midpoint, angle bisectors let us set up different types of equations. Equations that aren't necessarily based on the angle addition postulate, but with the relationship of these halves are equal, or this half is half of the whole, or the whole is, you know, double the halves. Like there's a lot of different relationships that we can set up that involve bisectors that are slightly different than just the angle addition postulate. When we say the word bisector, we always mean dividing into 2 congruent parts, whether we're bisecting a segment or we're bisecting an angle.